Change the exponential statement to the equivalent statement involving a logarithm. Our exponential statement is 4.3 equals 5 to the x. So in order to change this to a log expression or a log equation, we need to know the relationship between the components. So when we have a log equation like y equals log base b of x, this log equation has an associated exponential equation. The base of the log is the base of our exponential. So it's going to be base b. Then the log always equals the exponent. So y is our exponent. And then this expression equals what's inside the log. So this is how we change a log to an exponential and an exponential to a log by knowing this pattern. So for our example, the base of the exponent is 5, so that will be the base of our log, log base 5. The log always equals the exponent, so the exponent is x, and the log is going to equal x. And then our exponential expression equals 4.3, and that's what will be substituted inside the log. So log base 5 of 4.3 equals x is the equivalent log statement. Change the logarithmic statement to an equivalent statement involving an exponent. Our logarithmic statement is log base 9 of 729 equals x. So first let's look at the relationship between logs and exponentials. If we have a log equation like y equals log base b of x, the equivalent exponential equation would be b to the y equals x. Let's take a closer look. The base of the log will be the base of the exponent. The log always equals the exponent, and then the expression inside the log is what the exponential equals. So if we keep this pattern in mind, we can rewrite our log equation as an exponential equation. So the base of the log will be the base of our exponential. So we're going to have 9 as the base. The log always equals the exponent. So this log equals x, and that will be the power on our base. And then what's inside the log, 729, is what our exponential expression equals. So the equivalent exponential equation is 9 to the x equals 729. Find the exact value of a logarithm without using a calculator. This expression is log base 2 of 32. So the strategy that I'm going to use to figure out what this log equals is to first use a variable. I'm going to write my expression log base 2 of 32 and say that I don't know what this expression equals, so I'll use a variable p to represent what it equals. Now I chose p on purpose because p is for power or exponent, and the logarithm equals the exponent or the power. So it's going to remind me on how to rewrite this logarithmic equation. So to rewrite the logarithmic equation, I'm going to use the base base of 2 as the base of my exponential. The log always equals the exponent, so p will be my exponent or power. And then what's inside the log is what my exponential will equal. So now that it's written in exponential form, I'm a little bit more comfortable figuring out what that variable is. 2 to the p equals 32. If I can figure out 2 to what power equals 32, I figure out the value of p. So I know that 2 to the first power is 2, 2 to the second power is 3, not 3, 4. 2 to the third power is 8, 2 to the fourth power is 16, and 2 to the fifth power is 32. So that must mean that p equals 5. And now that I know that p equals 5, I know that my expression log base 2 of 32 equals 5. Solve the equation. Log base x of 121 equals 2. So this is a logarithmic equation because it contains a log. And one strategy for solving these logarithmic equations is to convert them to an exponential. So to convert it to an exponential, I would use the base of the log as the base of my exponential. The log always equals the exponent, so 2 will be the exponent. And the expression inside the log is what my exponential will equal. So now I have an equation with exponents instead of logs. X squared equals 121. I can solve this by taking the square root of both sides. The square root and the square cancel each other out. I'll gain that plus or minus symbol on the other side, and square root of 121 is 11. Then when I look back at my original with log equations, you should always check your work. So I'm going to check to see if 11 makes sense for this equation. Log base 11 of 121 equals 2, and that does make sense. Then I'm going to check x equals negative 11. That would give me log base negative 11 of 121 equals 2, and this is something that doesn't make sense. For logs, the only valid bases that we have are bases that are greater than 0 and not equal to 1. So negative 11 is not a valid base, and so we would exclude that from our solution set. So the only solution to the equation log base x of 121 equals 2 is x equals 11. Use properties of logarithms to find the exact value of the expression. Do not use a calculator. This expression is natural log e to the fifth. So for this example, I'll start off by using the power rule for logarithms. And the power rule says that if you have log base b of m to the p, so that means having inside the log some expression raised to a power, then you're allowed to rewrite that log as that power multiplied by the log. So I'm going to start this example out. Since I have a power on the expression inside the log, I can use that power rule to move the power in front of the log and make this natural log e, 5 times natural log e. And then these symbols, natural log, e, has the same meaning as log base e of e. So these symbols, natural log, is just a special way to write a log of base e. So let's try to figure out what that equals. If I want to figure out what log base e of e is, I can say that this is equal to some p for power. I can rewrite this as an exponential. That would be e, this base of e, raised to this power of p equals what's inside the log e. So it's this base of e to the power of p equals the e inside. So e to what power is e? That's e to the first power. E to the first power is e. So that must mean that p is 1. Log base e of e is 1. The equivalent way of writing that is natural log of e is 1. So natural log of e is 1. 5 times 1 is 5. So natural log of e to the 5th is 5.